Okay, hello to everybody. Good afternoon. This is the last session of the teaching training. Today is going to, now is going to talk Josep Calbo, who is going to talk about the specific foundation of environmental change. Remember, please, to turn off the microphones, and if you have any comment or question, you can write it in the chat. And at the end of the session, when the speaker finish, we can discuss with him all the questions or all the comments that you have write in the chat. You can use your language in French, Catalan, Spanish, or English, and we will try to help you at the end. So, Giuseppe, if you want to start, it's all yours.
Okay, thank you very much. Good afternoon, everyone. Yes, I must say that when preparing this presentation about this subject, which is titled "Scientific Basis of Environmental Change," I have had some doubts about what to present. So basically, what I've done finally, is base my presentation on the material which is written in the memorandum of the master's degree, and I tried to develop a little bit on this material. But of course, I think that the richest part of this session today will be the questions at the end, because probably you will have some questions or some comments that will go beyond what I prepared in principle. By the way, thanks also to everyone for being here with on Friday afternoon. So I hope that at least you can take some advantage of what I'm going to present now. Anyway, the title of this subject, the subject is titled "A Scientific Basis of Environmental Change." So more or less, with this title, probably you will have an idea of what is the subject about. It's about basically it's about the more, let's say, the more basic matters that frame the most environmental problems. I must say from the principle that from the beginning, that this subject was designed and is developed, at least here in the University of Girona, by a number of professors from the Department of Physics, which explains in some way how the subject is structured and is developed. In this first slide, I have put this picture of what are called the 9 planetary boundaries, because in some way the whole subject has actually the whole master's degree, but in particular this subject has to do in some way with this concept of planetary boundaries. From the physical point of view, most environmental problems have to do with the limits of our planet and global changes that are going on in the planet. So we spent some time talking about the planetary boundaries in the subject, and in particular, most of the subject is developed around one of these boundaries, one of these problems, one of these global issues, which is climate change. So as you will see, a good part of the subject is approaching climate change from different points of view and relating climate change with other environmental problems that are going on in the planet as a whole, and also in some regional areas. By the way, you can also take note of my email, because if in the future you want to contact me for any question regarding to this matter with this subject, you can write me an email to josep.calbo@udg.edu. Well, let me read the description of the subject, and I, while reading the description as it is written in the memorandum of the masters, I will make some additional comments. First, the subject begins with a discussion about planetary limits and growth, which justify the remaining content. This is, for me, it's quite important. This subject, at least here at the University of Girona, is one of the first subjects that the students follow. So the first few days, the first few classes are devoted to give a general frame of the global environmental issues. And to do this, I myself, because this part is developed by myself, I explain, or I talk about the general concept of the physical limits of the planet, and how this knowledge that the planet Earth is limited in some way, it has been approached in the last by different paradigms, different ways to approach these limitations in the last 60, 70 years. So we start with some documents from the middle of last century, and we end with some more modern approaches, like the concept of Anthropocene, or this concept of the boundary of the planetary boundaries. Then climate change is addressed, starting from a description of the climate system. So we describe the climate system, of course, because it's a comprehension of the climate system is necessary to understand also climate change. So this description of the climate system that contemplates the elements that constitute the climate system and the factors that make it up, including feedbacks, the energy balance, the greenhouse effect, and ocean circulation. So as you see, as I already told you, as you see, climate change and climate system, all the understanding of the climate system is important, very important in this subject, to understand climate change, the causes and the effects of climate change. Next comes the treatment of spatial and temporal variability, climate scales, and extreme episodes, and the causes and evidence of climate change. Yes, here an important point here is the understanding for climate change, but also for many, or for most environmental problems, the need to understand the different temporal and spatial scales involved. We think this is quite important to make students understand that environmental issues, environmental problems correspond to a particular temporal and spatial scale, but most of them are also connected with other temporal and spatial scales. So again, the climate and the climate change is a good example to talk about scales, temporal and spatial scales. Then attention is also paid to climate modeling, simulation, regionalization, and future scenarios and projections. Again, although we focus the attention on climate, it's a good opportunity to explain or to understand the concept of modeling a problem, modeling a system, in this case, modeling the climate. Modeling as an approach to a real system. The climate is a real system, a physical system, that we approach by mathematical models, by numerical models. So there are of course models, numerical models for many other systems, but the climate is a good example of this kind of models. Different levels of complexity of models, as we will see later. What models imply the need for data, the need for initial data for boundary conditions in some way. The understanding of different models for different scales. The need also to if you use models for future projections, if you use the models not only for understanding the current situation, but also for projecting future states, they need to understand the concept of a scenario, different possibilities, different ways, different paths for the future. So again, the concept is general, and the application in this subject is to climate and climate change. Then in the subject, we also address some effects on the natural environment, in particular in the Mediterranean context, such as water resources, land degradation, and desertification. Although this subject is not focused on effects, it's more focused on causes and understanding the system. But anyway, there is also this a few classes or a part of the subject about effects of the climate and climate change, but effects again on the physical system, not on the human systems, not on the ecosystems, mostly on the physical systems. Then in the subject that we teach here at the University of Girona, which by the way, it's a little bit longer, it's 9 ECTS, while the subject in the MEHMED Master is only 6 ECTS. In the subject that we teach here, as I was telling, we also include in the subject some classes about the ozone hole, which is another let's say global problem of the planet in some way, and we also connect with another issue, let's say, that is also connected with our expertise as physicists, which is this issue of the electromagnetic pollution, the possible electromagnetic pollution, so the pollution of the possible effects of these growing abundance of electromagnetic waves in our environment. Again, I want to stress that as I already told you, that the subject matter is taught by a number of professors. So I think right now we are 5 professors of the Department of Physics. Of course, the approach from a physicist point of view may be different from the approach of other backgrounds. So if this subject is taught by other backgrounds, probably the approach details may be different, but the general idea could be more or less the same. The idea of making students understand these physical limitations as a general concept of the planet Earth, how stressing these limitations, how humans are forcing the systems, how humans are perturbing the let's say the equilibrium, more or less a stable state, and how due to this forcing these stresses that human beings are putting in the system, in the Earth, in the planet Earth system, we are maybe the planet as a whole is living from the equilibrium that it was previously more or less stable. This is what is shown in this image. This image is taken from a paper about this concept of the Anthropocene, the concept that is related with this enormous impact of the human beings through our industry, our growth, our resource use of resources, etc. So although the concept is relatively complex, let's say that the idea is quite simple. The idea is that the Earth as a whole was more or less in a stable state here in this ball, in some way, in this Holocene state in the last more or less 10,000, 12,000 years. The Earth has been in the more or less in the same climatic state, and in other matters also, in other biogeochemical cycles and other aspects, has also been more or less in an equilibrium, in a permanent state, only with small perturbations, small changes around this equilibrium state. This is what's called the Holocene, the geological era where we are right now. But due to the human pressures, due to the from the agricultural revolution and then the industrial revolution, and now, I mean, of course, the demographic expansion, etc. Humans are putting a lot of pressure, a lot of stress on the system, and probably the Earth is moving away from this static equilibrium, and maybe in the future the Earth will be in a different equilibrium, in a different state. So this is also a general concept that in the case of the climate is quite easy to illustrate. According with the description of the whole masters in this subject, we should develop, or we should address these competencies. Three transversal competencies and three common specific competencies, which are this in total these 6 competencies. This subject should help in developing the competence of obtaining and selecting sources and information using ICT. This, I mean, in some way, indeed, we use information and data and tools that are found on the network, on the internet in general. So this way we develop this competence. Also, the second competence about communicating information orally and in writing with well correctly developed arguments, and so this competence is developed through basically through some assignments that we give to the students, in particular writing assignments. I will explain a little bit more later. And the other competence, the general or transversal competence about analyzing new and complex situations and designing possible solutions. In particular, from this general competence, we address here complex situations. Climate system is a very complex system that is also connected with other global problems. So we show this, we try to show all these connections, all this complexity. Regarding specific competencies, this subject should help developing these three competencies: analyzing and interpreting the processes of change and environmental conflicts, applying again the concept of complexity. I already talked about the complexity concept. So, and of course, we analyze a lot climate change, which is one change that is going on in the Earth as a whole. So it's clear that this competence is developed in this subject. The second specific competence is the student should be able to analyze and interpret the mechanisms of response and management of environmental processes and changes in a manner with well thought out arguments according to the conceptual frameworks of various disciplines. Well, this competence is quite general, and I think that we here our let's say contribution to this competence is allowing students to be in contact with the point of view, the way that physics and physicists approach these environmental problems. And the third specific competence is about building scenarios and planning environmental policies aimed at the recovery and protection of the territory and water or air. In this case, again, maybe our specific contribution is about this scenarios concept in particular. So indeed, the subject has to do, as it must be, with the competencies that are assigned to this subject. Let's go with the detailed content of the subject. This is the content that we propose, that we suggest. Of course, I understand that it may be more or less slightly modified or slightly by any in the particular development of the matter of the subject in each university, or depending on the kind of professors that develop it. But anyway, let me go through this detailed content, and also to adding some comments during the as I told you, that first we start with these general concepts of environmental change, causes and evidences. We talk about the limits of growth. This concept that for me is quite important. And we start with very, relatively old documents. The old, one of the oldest documents about these limits is the document by what is called the Meadows Report, a document from the 1970s, which is titled exactly "The Limits of Growth." So where the authors start to said that Earth is a limited planet, so there are limits for growth. So this is a relatively easy concept for a physicist, I would say, but it's a concept that must be understood by everyone working on environmental issues, because as I told, many environmental issues come from the idea that the Earth is so big that it can deal with everything, and this is not the case anymore. It's important to understand the concept of exponential growth and the concept of the difference that there is between sustained growth and sustainable development. Similar words, sustained growth with sustainable development, but despite being similar words, very different ideas behind them. The sustained growth is unsustainable by itself. So we must understand that the concept of sustainable development is not the same than the concept of the sustained growth that sometimes economists or other areas of even politicians follow or mix. I think that's important also to introduce the concept of Anthropocene. It's just this idea that the humans are interfering so much on the planet Earth as a whole that we are changing the Earth, and that maybe in the future, in the long future, the humans of the future will see this time as a time for a new geological era, because of the big impacts that we are producing on the Earth system, including extinction of species, including the enormous change of the content of CO2 in the atmosphere, or the radioactive footprint in sediments, for example. And then we explain also this relatively modern concept of planetary boundaries, including the climate change, but all other planetary boundaries regarding the freshwater use, the ocean acidification, regarding the perturbation of several biochemical cycles, regarding other pollution, regarding biodiversity change, etc. So the planetary boundaries is a way to introduce students with the main global problems that in most cases are also have also a reflection, or have also are also problems in local or regional scales. The second topic of the subject is a short topic. Actually, we only spend with this topic maybe a few hours. I don't know, 2 classes, which means 4 hours of class and maybe 10 hours for students or less. It's about paleoclimatology, basically to give an idea of that the climate is changing now, but of course climate has been changing in the past too. So students must know that climate has changed in the whole history of Earth, but this knowledge is necessary to understand why current climate change is different and why we are concerned about current climate change. So it's good to know that climate has been changing in the past, but the main point here is that the changes in the past have been much slower than current change, and changes in the past have been produced by, let's say, natural factors, changes in the sun energy emission, changes in the Earth orbit, changes in volcanic activity, changes in the distribution of continents, all changes in the past have some kind of natural origin, but all of them are much slower than current one, because current climate change is due to human impact and is extremely fast in geological scale. So it's good to understand how current climate change differs from former, let's say, geological scales climate changes. This is the content or the goal of this second topic on paleoclimatology. The third topic tried to set the basis, the basics of the climate system. So it's a topic about how the climate works, how the climate system behaves, which are the reasons for the climate that we enjoy in Earth. So this is there is some basic physics here. So about radiation, about energy, about basic physical concepts that we try to develop, as our students are not physicists. We try to develop in a quite conceptual and let's say simple way, but trying to make these concepts to be understood, because they are important concepts. The concept of the radiation balance, the concept of energy balance, the concept of circulations, the atmospheric circulations, the ocean circulation. So all these concepts that conform, that drive the climate system. So of course, first we start introducing what is climate, then fundamentals of radiation, some fundamental laws, the greenhouse effect, a very important effect, a very important factor for understanding the climate of the Earth. Then we try to explain the importance of the atmospheric circulations on the climate of the Earth, the concept of relative forcing. So how when some factor in the climate system, the most important one being the concentration of several gases in the atmosphere change, these changes produce a change in the radiation balance. So this is called the radiative forcing. So this is also a very important concept. And also very important concept is the concept of feedbacks. Climate system not being a linear system, but a very complex system with where some nonlinear feedbacks have an effect. So the importance of understanding that the response of the system is not always directly proportional to the cause of the system. There is also a part in this part of the subject in this topic that where we talk about the emissions, because the emissions of greenhouse gases are the cause of climate change. So we talk about how to compute emissions globally, but also at the different scales, regional scales, even at the individual scale. Actually, in this topic, we suggest an exercise for the students, where students make an estimate of their own climate or climate footprint. So they estimate the amount of CO2 that they emit in 1 year or in 1 week of their activities due to their mobility, due to their use of heating and cooling, etc. So there is an exercise for them to study the emissions of greenhouse gases. The fourth topic in the subject is again about the climate system, but specifically about the importance of the ocean in the climate system. So we devote a particular subject, particular topic about on the ocean circulations and the role of oceans in the climate system. Usually, we think, I mean, most of us may think that climate is related with atmosphere, and it is indeed. Atmosphere plays a very important role, but oceans play also a very important role because oceans accumulate, may store a lot of heat, and also because oceans work as a way to move heat, to transport heat from one part of the Earth to other parts. So ocean circulations are very important to understand the climate system, to understand the climate of the Earth, and to understand the possible answer, the possible response of the Earth to this human forcing on the climate. So in this topic, we talk about the oceans and climate system, what is called the thermoline circulation, these mechanisms of heat transport in the ocean. Is also there is also some time devoted to ocean acidification, which is not directly related to climate, but has also something to do because it has to do with the absorption of CO2. So, and finally, the importance of ocean to connect the climate in different parts of the Earth, what's called as teleconnections or oscillations. The fifth topic of the subject is focused on climate modeling. So in explaining what is a climate model, how climate models, I mean the concept of climate models, and to show different types, different kinds of climate models. There are very quite simple climate models. Actually, at the end of this presentation, I will show you one of these very simple climate models, but that, despite of being simple, are I would say interesting because conceptually these simple models may be understood by students quite easily. So it's a first introduction, a first contact with models. So as I told you before, for us, showing these models here is a way to introduce the concept of models for any system with the particular example of climate change, So we show what's called zero-dimensional models, one-dimensional models, and then also we explain the complete, the three-dimensional models, which are the models that are used by the IPCC, by the governmental organs to produce their policies and to assess the future climate change. We explain how these models are used for projections, for projecting the climate. So how these models are used to try to estimate how the climate of the future may be. To do this, we have to introduce also the concept of a scenario, as we don't know how the future emissions will be. So we when analyzing future climate projections, we base these climate projections on different future scenarios of emissions, of different scenarios of amounts of greenhouse gases emitted in the atmosphere. So it's also the concept of a scenario and the use of this concept in this frame of climate and climate change. It's also important to make students understand that all these models bring uncertainties with them. The concept of uncertainty it's also a complex concept, but important concept, because we know, I mean, future projections are uncertain, of course, but this uncertainty is inherent to all prognostics, to all projections. And the uncertainty should not be an excuse for not acting, for not taking measures. So, despite the uncertainty, we have to act. We have to take some political measures or economic measures, social measures, etc. So, this the understanding of the concept of uncertainty is also very important, we think. We talk about downscaling these projections, as most models, climate models, are global models, so give as a result projections for the climate of the whole Earth, the whole planet. But for regional policies, we need more detail at regional or local level. So there is a lot of there is a good deal of techniques to downscale, to give more detail to these global simulations. This is called downscaling techniques. So we talk about downscaling techniques, about regional models, and after talking about all these techniques, we explain also some results of these models. How the current models project the climate of the future at the global scale in these IPCC reports, and then also some regional projections, in particular for the Mediterranean, and in this case of Girona, for our area of Catalonia, but this can be applied to any other area in the Mediterranean. The sixth topic of the subject is about focus on some effects of climate change in the Mediterranean, in particular the possible impact of climate change in coastal areas, of course the impact on rising temperatures, on changing rainfall, etc., and on water availability, and the consequences on, for example, for desertification of some areas, etc. But the idea is to give some attention to which may be the consequences of the climate change in our Mediterranean areas. Then, although these other topics are not included in the description of the matter, I just put it here because we also had these three additional topics in the way we develop the subject here at the University of Girona. We take some time also to talk about the ozone hole, which is, as I told you before, is another global problem. We also have some classes devoted to the electromagnetic pollution issue. And finally, we also approach from the point of view of physicists, we approach the problem of the, let's say, migration of species, of natural species, of different animals, different plants that are changing their distribution on Earth. So all this matter of invasive species, which is approached by our biologist colleagues, but there is also an approach that is applying some physical, let's say, equations, physical techniques, in particular the diffusion equation, to these natural invasions of natural species. So I leave it here just in case, in the adaptation of this subject to your particular context, your particular university, you may want to add some of these additional topics. Well, how we develop this subject by using several different, let's say, methodologies, pedagogical methodologies, which are, I mean, quite known by you probably. So I don't want to spend a lot of time here. We use of course lectures, traditional lectures, to present the most important, let's say, concepts, and to develop the basics of the several questions. But we try to work in several practical sessions too. So suggesting, proposing exercises to students, and working with them in some particular exercises regarding the climate system, regarding the emissions of greenhouse gases, regarding climate models and results of climate models, regarding ocean circulation. All these specific matters, we suggest some particular exercises with some, let's say, quantitative content. So the use of some equations, simple equations, and some quantitative analysis of the systems. We also suggest the students, provide the students with some texts, some papers, for example, that they have to read and analyze and comment. And also we suggest them some graphical documents, let's say some documentaries or some online conferences or online seminars, etc., that they have to follow, they have to look at, and then we make some questions for them to answer and in relation to these papers or these graphical documents. Every year we try to invite some external professor to give 1 or 2 seminars in order to enrich the subject. So if we bring to the subject to one researcher from another center or one professional who is working in these matters, in climate or climate change, but from a different point of view, that we think that this makes the subject richer, more interesting. One of the assignments for the students is like a final work, a final project, which must be developed by a group of students. So in this way, we force students to work in groups of 3 or 4 people, which is also interesting when these different students have different backgrounds. So if we can mix one biologist with one geographer, one engineer, working together in a particular subject, they learn from each other and they can produce some interesting project, let's say a simple project, but anyway, some kind of particular study. In some classes, we can generate a debate. So we ask students to prepare some matter and prepare a debate about some particular question. I don't know, for example, about CO2 greenhouse gas emissions and how to mitigate them, for example. So instead of the teacher explaining the solutions, we ask them for thinking about solutions, and they debate among different, let's say, conceptual ideas, or even sometimes ideological ideas or positions about some issues. Of course, the students can at any time contact the teachers, professors, to clarify topics or to improve their understanding of some matter during these tutorial sessions. Regarding the assessment and marking, this is the distribution of the let's say the weight of each kind of assignment in this assessment of the students' work, let's say. So a good part of good fraction of the final marking will be related with the exercises that we assign to them, these quantitative exercises, let's say, including exercises related with climate models. Then we also give quite a big part of the marking to this group project, this group work. We suggest several topics. They choose the topic that they want to work on, and then we assess this work basically based on these different aspects. I mean that in this work, of course, the content is important, but it's also very important that the way they present the content, the capacity that they show in finding different sources of information, how they use the bibliography, the references, how they integrate different references, how they also add some personal criticism of personal ideas. So this is not a research project, of course. This is just let's say a bibliographic study. But so we when we mark this study, this project, we assess these different items. Finally, also we also assess and give some marking for this let's say, short assignments about some particular papers or documents that we give the students for them to read or to watch and to comment. And also we assess their participation in this debate that we suggest. Yeah, I am close to the end of the presentation. Here I'm just putting some links to some materials that I use sometimes, or I suggest students to use. In particular, all these first links are to different, let's say, important, quite well-known authors, authorities in the matter of climate change, planetary boundaries, these concepts that they have given some talks. All these links, I think, correspond to what is called TED Talks. I don't know if you can see them. Let me anyway. Let me see if you can see them. These TED Talks are 15 minutes talks, which are given by very good presenters, and I like the students to watch them because in 15 minutes they receive a lot of information that they can further inspect after watching these talks. So of course, here I only put 6 or 7, but there are lots of them, and you can find lots of them in the internet. So using all let's say material that there is online, it's a very good way to complement our classes. And then regarding the use of data and information about climate and climate change on the network, there's also lots of pages that of information on the internet. For example, I show them some kind of pages like this or tools like this one. This is about let's say an online climate model, which is a very nice to play with, let's say. So I encourage them to go to this page and try to use this tool to understand how the climate works. I mean, this complements our classes. This is after we have explained all the elements of the climate system, the importance of the shortwave radiation from the sun, the importance of the infrared radiation from the air, the importance of the albedo of the clouds, the importance of the oceans, the importance of the greenhouse gases in the atmosphere, and so they can play with all these factors here. They can see the effect of each of these factors. So there are other tools like this, but this is one that I use several times and is quite nice tool. There are other tools. For example, tools to, let's see if I can go to this one, to see let's see, some tools to visualize climate change projections. So when we talk about the climate models results at a global scale, these climate models give huge amount of data, of information, this data is difficult to let's say to reach and to take and to analyze, because they are really huge files. So for this kind of students and for this moment of their learning, seeing the results in a visual way and in a simple way is quite interesting. So this is a tool that you can play with different models, with different variables, temperature, precipitation. You can choose different scenarios of the climate for the future. So there is a lot of information behind of this visualization, but the visualization is very clear for the students to show the effect of different scenarios, different models, different projections, etc. So there are lots of these tools. I just put here a couple of them. Sorry, I'm going back to the presentation. Okay. Okay. And then, well, I don't know if I had prepared like also example of one of the exercises that I work with the students. I don't know, Marta, Josep, if I should. I mean, I have 10 more minutes or 15 minutes to explain this exercise, or you prefer that I stop here and go to the questions?
No, you have time, so
okay.
It's no problem. If you want to continue, it's okay.
Okay. Yeah. Before finishing, I had just prepared one of the exercises that I assigned to the students regarding the climate system and particular this climate modeling. The idea is that the climate system may be summarized in this. Maybe summarized in this scheme. This scheme is a summary of the whole climate system. Of course, the climate system is, as I said to you before, is extremely complex. We could talk hours and hours about the climate system, but a good summary of the climate system and of the main elements of the climate system is this scheme, where as I'm saying, the main elements, the incoming solar radiation, which is the drive of the climate in some way, the amount of radiation, the amount of energy coming from the sun, is the main drive of the of the climate system. How this solar radiation is distributed in the atmosphere, interacts with clouds, with aerosols, with gases. How some part of this solar radiation reaches the Earth, hits them. Some part of this radiation is reflected by the Earth. So all the interactions of the solar radiation with the Earth, this is the very important element of the climate system for understanding the climate of the Earth. And then a second element equally important is the emission of what is called terrestrial radiation, infrared radiation. The Earth is hot in some way, so the Earth emits also radiation back to space, but this radiation, this infrared radiation, interacts also with the atmosphere, interacts with clouds, with gases, in particular with greenhouse gases. So only part of this radiation emitted from the Earth reaches the space, because a lot of this radiation is absorbed in the atmosphere. Sorry, I can't remove this pop-up. Sorry. I think. Oh yeah, okay, I could. Okay, sorry. So I was saying that the infrared radiation emitted by the Earth is in part absorbed by the atmosphere, and the atmosphere emits back to the Earth. This is what is called the greenhouse effect. Part of this radiation escapes to the space. Shortwave radiation and all interactions, infrared radiation, and all of interactions with the atmosphere, and then also two additional elements which are called the sensible heat and latent heat. So another way to transport heat from the Earth into the atmosphere. Well, this is, of course, when I show this scheme and when I explain this to students, I use more than 1 hour to explain all this scheme, all the elements, all the factors. But here, just to give an overall idea, the idea of the climate system is that all these fluxes are in equilibrium. So the Earth is basically in equilibrium. So if you look at these numbers, the total incoming solar radiation that reaches the top of the atmosphere, this 342 watts per square meter, is in balance with the amount of radiation that is reflected and the amount of radiation that is emitted by the Earth. So this is in equilibrium as it does as the surface. The Earth's surface is also in equilibrium. All the incoming fluxes are in equilibrium with outgoing fluxes. So we say that the climate of the Earth is the result of this equilibrium, of this balance between all these, among all these different fluxes of energy. Then how can this be modeled? How can this be analyzed quantitatively in order to study how the climate will change if some of these fluxes, some of these effects, some of these interactions change? Excuse me. Well, to do this, we have a model. And a model is something like this, as simple or as complex as this, depending on your background in some way. But here, this scheme is basically the same scheme as in the previous slide, but where all fluxes are represented by a symbol or by an equation, let's say. So the amount of solar energy from the sun is this symbol, and the amount of energy emitted by the Earth is this equation, which is the Stefan-Boltzmann equation of a black body emission. The absorption in the atmosphere is parameterized by this factor, the absorptivity of the atmosphere. The albedo, so the amount of solar energy that is reflected, is parameterized in some way by this factor, the albedo of the surface, etc. So all these different fluxes from the previous slide are represented by the corresponding amount symbol equation that parameterizes or that represents these fluxes. And as I told you before, these fluxes are in balance, are in equilibrium in the top of the atmosphere, in the surface level, and also in the atmosphere as a whole. So we have three different balance equations. This is the balance of the atmosphere, the equilibrium, the balance between the absorption of heat in the atmosphere and the emission of heat, of radiation in the atmosphere. This is the second equation, is the balance in the surface. The surface of the Earth is in balance, should be in balance, in equilibrium between these the incoming fluxes and the outgoing fluxes of heat. And then also the top of the atmosphere, the planet as a whole, is also in balance between the incoming flux, which is the only incoming flux, which is the radiation from the sun, and the outgoing fluxes, all these fluxes that are leaving the atmosphere. So these are three balance equations, three equilibrium equations. So we have here, and this is what we explain to students, that all models are more or less like this. Models for any system is, you have to understand the system, you have to understand the main elements of the system, you have to parameterize them to use the laws of the physical, chemical, or biology laws in a mathematical way let's say, to quantify all these different factors, and then apply some equations regarding to the behavior of the system. In this case, the equations are balance equations, equilibrium equations, because the system is in principle in equilibrium. The idea of this model is actually quite simple. This model may allow us to compute the temperature of the Earth's surface, which is called TA. This TA is the temperature of the surface, the temperature that we enjoy in some way at the surface, at the ground surface, let's say at the Earth's surface, and also the temperature of what's called the temperature of the atmosphere. The surface is TS, and TA is the temperature of the atmosphere. There are two temperatures here: the temperature of the surface and the temperature of the atmosphere. So these two temperatures may be computed from as a result of solving these three equations. Actually, we only need two of them, but anyway. So by changing some of these parameters, we obtain different results. For example, if we change the emissivity of the atmosphere, this epsilon sub A, this emissivity of the atmosphere, the temperature will change. And the emissivity of the atmosphere depends on the greenhouse gases concentration. So if we change the amount of greenhouse gases, we change the emissivity of the atmosphere, and we change the climate, we change the temperature, and so on. If, for example, if the sun, by any phenomena, for example, in a geological scale, the sun changes a little bit the output of energy, then less or more sun will solar radiation will reach the Earth atmosphere, and if we change this input, the amount of solar radiation coming from the sun, of course, temperatures will also change. So a model is a way to represent the system, and is a way to play with the system, changing some input values. We can get the output, different output responses. And this is what we suggest to students, to use this model, these equations. We ask students to use this model to answer several questions. We suggest these 9 questions, but with this model we can answer many other questions. The way we work with them is that we provide the model already, let's say, code or programmed or developed in an Excel worksheet. So let me show this Excel worksheet just for you to see how we work with the students. I mean, in this worksheet, students basically see this page, that we call it this control page in some way. There is several cells, this blue color, that we can change. And when we change any of these different input values, the model computes the output, so the temperatures, these temperatures of the atmosphere and the temperatures of the ground surface, of the Earth's surface. So for them, it's relatively simple. For example, right now, this is the first values, the values that are set as default, are the values corresponding to the pre-industrial conditions, and give the mean, the average Earth temperature for these pre-industrial conditions. But for example, if we change the amount of CO2 to the current level, currently we have 411 ppm in the atmosphere, then the model computes new temperatures. Of course, 411 ppm is more CO2 in the atmosphere, more greenhouse effect, so the temperature of the surface increases from 14 point something to more than 15 degrees Celsius. We can change this one or other inputs, and we can also activate or turn off several feedbacks. For example, right now, all important feedbacks like the water vapor feedback, the ice albedo feedback, and the sensible and latent heat feedbacks are turned off. If we turn on these feedbacks, then again, temperatures are recomputed by the model, and we see the effect of these feedbacks. So, for example, with the water vapor feedback, the temperature increases a little bit more. With the ice albedo feedback, the temperature increases a little bit more too. So it's a way to show students that the climate response, so the temperature in this warming climate, in warming conditions, is the result of this increasing CO2 or increasing greenhouse gases in the atmosphere, but also this response is enhanced by some positive feedbacks. Actually, the third feedback, the feedback of the sensible and latent heat, is a negative feedback, and you will see that the temperature now is a little bit decreased. So we set several questions, and they have to play with this model just by changing the input values and changing this activation or this turning on or off these feedbacks. So the exercise is relatively simple because what is more difficult, that would be more difficult, would be to translate, to transport the equations into the Excel or Excel worksheet, or into I don't know, Python or Fortran code. But we make this for them. But we also show where are all these computations. These computations are in this second sheet. So for students that are interested, they can go to this second sheet and see how all computations are produced, are developed in this second. Yeah, I mean that there is there's quite a lot of computation behind the result that is in this yellow cells. So for them, the exercise is more exercise of using a climate model, using and interpreting, because when we mark this exercise, of course we give a lot of value to the interpretation of results, because getting correct results is very easy. They only have to change the numbers here, and the result is correct always. But for us, what is important is how the students interpret and understand the results. How they interpret that when we increase the amount of CO2, temperature increases. When we turn on the ice albedo effect, temperature increases more, etc. So in these assignments, we ask students to give the results of the model, in this case, but in particular to give their interpretation of the results, why the climate behaves as it behaves, and depending on these different changes. So this is a sample, one example of one exercise. We suggest this kind of exercise with other climate models, with a little bit more complex model, which is a one-dimensional model, and with other models and with other areas of the subject, with for ocean circulations, for CO2 emissions, and so. As I said, the question that we suggest for this particular exercise: how the global temperature change when we change the albedo, how the temperature change when we change the solar radiation absorption, how the temperature change when we change the sensible latent heat, and so on and so forth. How the feedback of water vapor acts, how the feedback of combination of feedbacks of water vapor and ice and albedo. So several questions, and we could even generate more questions. And I want to insist that in this case, and in many cases in this subject, it is even more important the understanding, the way how students explain the results, that not the results themselves. Well, I think that I think that I reached the end of what I had prepared for you today. And now it's time for your questions. If there are any of them, we'll try to answer them. Thank you.
Thank you, Josep, for your presentation. I don't know if you can see the chat. You have one question in the chat, and then all the participants, you know that you can turn on the microphones. And if you want to ask something to Josep, this is the time to do it. And then, Josep, I don't know if you can...
Yes, I can see the chat. Yeah, I can see the chat. And I see that the question that there is right now is about the research subjects or topics at UDG in relation with what you kindly... Thank you for your words. Yeah, so you mean that how this subject is related to research research at the University of Girona. Yes, most of this subject has some relation with research of some groups. Actually, most research is developed by my own group. I am a member of a group, a research group, which is called Environmental Physics Group. In this environmental physics group, we are like 7-8 professors, and all of us work on either on air, atmospheric sciences, let's say, atmospheric physics, or on water physics, either on continental waters, so lakes, rivers, or in oceans, so oceanography, always from the physics point of view. So we have developed, and we developed some research regarding, for example, ocean circulation, atmospheric circulation, and in my particular case, with one colleague, we focus our research on radiation balance, on the interaction between solar radiation and infrared radiation with clouds and aerosols. So yes, our research is quite related with this subject. We have to. I mean, I have to recognize that, for example, we don't develop complex climate models. The complex climate models, what they are called the general circulation models or global climate models, ocean atmospheric circulation models. So the climate models that are currently used by the governments, by the IPCC, by the UN, etc., are models very extremely complex that are developed only by very, let's say, top institutions, which have huge, big teams of people, of researchers, coming from the atmospheric sciences, from the oceanic sciences, from computation sciences, from mathematics, from chemistry, from biology. So they form very big teams that develop these complex models. So at the University of Girona, there is no one developing climate models, but we are using, and we work in our research, and also in some, for example, PhD thesis, and even in master's thesis, we work, we do some research using results of climate models. So we are relatively used to work with climate data and climate results, climate projections from the user point of view, which I think is important for the students, because most of our students, I would say that they will be users of climate model, climate data and climate models projections. They won't work in climate models development, but they will work as users. So I would, as I say, most of this subject is relatively close to our research. Yes, I see some other questions. One is, yeah, are you developing yourself the presented model? Yes, as I was telling, we are not working in these complex climate models, three-dimensional models, which are very, very complex and need a lot of human resources. But yes, I let some way this climate model that I show, and also the one-dimensional climate model that I use in my classes, was originally developed by a colleague of mine from another university, another Spanish university, and I took this his development and I just added some additional development. But these are very simple. Actually, these are you've seen that these models, these zero-dimensional and one-dimensional models, are just a few set of equations that can be quite simply coded in a program, in a code, in a Fortran code, or in an Excel file. So yes, the simple models have been developed by myself with help of other colleagues. The other question is about the chemical atmospheric reactions. Good question. We in this subject we do not let's say deeply explain the chemical part of the problem. Let's say, of course, there is chemistry involved. There is chemistry involved in the conversion of some emissions in the atmosphere in some gases in other gases, in the decay of some gases, methane, for example. But we don't explain this I mean, we explain this, but not in a deep way. Why? Because we are not experts, I must say. That's the first reason. Second reason, because in general, this is a second order importance for the climate system. As soon as you have fixed the amount of these greenhouse gases, the most important greenhouse gases have a quite long residence times in the atmosphere, so they don't decay rapidly. So from the climate point of view, the chemical reactions are, let's say, a second order effect in some way. From pollution point of view, these are very important. One exception being the ozone hole, and actually, actually the other question is also about the ozone layer. Of course, the ozone layer does have a relatively rapid cycle, an annual cycle, so a shorter time scale compared with the cycle of CO2 or methane. And when we explain the ozone hole and the ozone layer issue, we explain with more detail the chemistry, of course, the chemistry of ozone, oxygen, chlorofluorocarbons, nitrogen oxides, and all this cycle of catalysis of ozone and oxygen. So in order to understand, to explain the phenomena of ozone hole, we have to explain some chemistry there, and we explain that chemistry there. The question about the units, maybe I don't understand this question. The evaluation of the ozone layer, the depression, use very specific unit system. Actually, the ozone, the stratospheric ozone is usually measured in Dobson units, which is it's a way to measure the whole amount of ozone that we have over our heads in some way. And this Dobson units is the standard units that are used for the ozone, the stratospheric ozone measurements. So we explain also the meaning of the Dobson units when we explain the ozone hole and the ozone problem. Yeah, there's a question about that having this. I understand the presentation available for all the people attending to this seminar. I don't know. Probably the organization will take care of this.
Yes, we will give sorry, the presentation to all the participants. So don't worry, Saliha, because you will have it. We will gestionate that.
Okay.
So I don't know if anybody else has another question or want to turn the microphone on or write it on the chat.
Excuse me. Could you hear me, please?
I think we cannot hear the question. Maybe, Josep, if you hear the question, you can repeat it or write it in the chat, the person that is talking.
I am not talking about the presentation. I am talking about the use of these models. Is it possible?
Yeah, the question is about the use of the models, not about the presentation.
Okay.
De mettre ces programmes à la disposition.
Yeah. Okay. The programs. I understood the. Sorry. I had understood the presentation. Okay. You mean the models? I would say so. I mean, I don't have any, let's say, copyright on them, so I would say that I could also send these Excel files to you, and you could maybe translate just the names in your languages, and I think you could use them. Let me just check that there is nothing left on them that may be protected in some way, but in few days I would send them to Josep or Mita or Marta, and they will share the codes with you. Yes. And yes, Hatem is saying that they are available on the internet. Yes, okay. I mean, some of them. I mean, there are climate models on the internet. Actually, that link that I showed you from the Monash University. Sorry, going back. This. Let's see if you can see this one. Oops. Can you see this one now? Can you see this one? Yes, okay. So this Monash simple climate model is available on the internet. Yes, so you will have the link from my presentation, and this is a very nice model. You can spend a lot of time with it. There are even some games in the page. Several questions. You can use it in different ways. So this is available on the internet. It's a very good. I would say that's quite a good tool. There must be other similar, but the specific this zero-dimensional model that I show you on the Excel file, and another one-dimensional model that I use and that I also have programmed in an Excel file. I think these are not on the internet. They are let's say they are only my computer and some of my colleagues' computer, and they are not available on the internet. So I can share them with you. But of course, there are several tools on the internet.
Okay. I don't know. Somebody else want to ask something?
I want to add something from my side.
Okay.
I want to say thank you very much to Josep Calbo, because in the presentation we are not explained that he is the vice rector of strategic projects of the University of Girona. So he has a very busy agenda, but finally he found the time to be with us. So Josep, thank you so much from our side. In fact, 3 vice rectors was involved in this teacher training. So I want to say thank you so much to the responsibles of the university for his involvement in this teacher training. Thank you so much.
No problem, Josep. Thank you for inviting me. Actually, it's a coincidence that 2 vice rectors are quite involved in the master's degree,
yeah.
And the other one is very involved in this ICT teaching question. So it's a pleasure for me. I mean, I think that this project, this capacity building project, is very important for the university, for the University of Girona, and of course for all universities participating. So for me, it's been it's a bit tough to prepare the presentation, but it's also been a pleasure to be with you today. And again, if there is another question in the future, you can reach me by my email or through the coordinators of the program.
I saw there is another question.
Yes, and we have time, so if you...
Yeah. Sorry. Wow, this is a very technical question. Yes, actually, we explained some of this isotope analysis regarding different oxygen isotopes or other carbon isotopes or thorium, this kind of analysis. We explained something about them in the part devoted to paleoclimatology. So indeed, to study paleoclimate, so climate of the past, we explained some of the techniques that are used to know, to estimate how was the climate of the past. So yes, we explained something about the isotopic techniques.
Okay. Everybody is saying thank you for your presentation, Josep.
Okay.
Thank you very much.